So today we are going to talk about the effect of air density on aerosol transport velocity capability in a local exhaust ventilation system. Okay. So to control the exposure to chemical hazards, wet methods can be used, but local exhaust ventilation system (LEVs) are the engineering control of choice for the exposure control of most chemical hazards in the work environment. To put us into perspective what the study is about, we are going to discuss some relevant industrial ventilation concepts. Basically, air density depends on temperature. The higher the temperature, the lower the density. Elevation, the higher the elevation, the lower the density. Absolute humidity, the higher humidity, the lower the density. And for industrial ventilation purposes, the duct static pressure, higher static pressure, the higher the density. So the worldwide reference manual for design LEVs is the Industrial Ventilation Manual of Recommended Practice and Design. We are now in the third edition, and the current recommended method for design LEVs is the velocity pressure method. So the two primary parameters for designing industrial ventilation systems are the minimal transport velocity, MTV, and the hood actual flow rate. We know for a fact that the current design method is quite effective for systems operating close to standard environmental conditions. So what triggered our interest in this study? So we know several colleagues who are working in mines in South America at high elevation and others working near sea level, and they have to extract contaminants from different type of process. Some process were performed in very hot and humid environments. There are a few problems identified by industrial hygienists in this work environment. As you can see in the picture, there is an industrial ventilation duct filled with material. It should be perfectly clean. We have this problem even though the systems are being designed with the traditional method. So when the particles are collected in local exhaust ventilation system, it is extremely important that they effectively move to the system, to the air cleaning device. If they don't, we have problems which negatively affect worker health and safety. So duct settling has been traditionally attributed to improper initial design and maintenance and original system design alteration once the system was correctly implemented. But what about the effect of air density? We reviewed publications from 1935, and none of them take in consideration air density as important design parameter. So we designed a study with two key hypotheses. The first one, if we maintain air velocity constant inside the left system and we operate them with different air density, as the air density decreases, the air will have a lower ability to push contaminant through the ductwork, and there should be more sealing inside the ductwork. And the second one, if we maintain velocity pressure constant inside the LEV and we operate it in different air density, the amount of contaminant sealing inside the ductwork should remain constant in respective of air density. So based on our hypothesis, our research team designed a real local exhaust ventilation system, as you can see in the picture. Our experiment was originally conceived to test two design methodologies. The first one, constant velocity, and the second one, constant velocity pressure. And were tested at 5 different elevations and evaluated 3 times in each evaluation. Our response variable was conveying efficiency. Design parameters were controlled through continuous static pressure monitoring. So, as you can see in the scatter plot, as the elevation increased, our total density factor decreased. The red dots are constant velocity. As you can see, the conveying efficiency decreased significantly with density, which coincide and correlates with elevation. Velocity pressure maintains almost constant for the entire density spectrum. Here we can see an interval plot, 95% confidence interval for velocity on the left and velocity pressure on the right, showing that our velocity pressure hypothesis is more appropriate for their design. So we recommend constant velocity. We recommend against constant velocity as the design parameter to keep the contaminants from settling into the ductwork. We recommend velocity pressure as the design parameter to keep contaminants from settling in the ductwork. So the LEV system should be designed based on a density at just minimum duct velocity. Here, acknowledgement to the intellectual contribution, Mr. Jonathan Hale, Mr. Robert Dave Ringer, and Dr. Sergio Caporali, in addition to Mr. Dylan James and Mark Pabol. Thank you for the 3D drawing, Mr. Bill Howard. Thank you for all the sponsors. We dedicate this study to the positive impact generated to the worker health around the world to Mr. Patrick Curran, CIH. Thank you.